The format of the talk is, I divided it into 3 parts, and the first part is just sort of general and philosophical stuff that I tried to keep completely non-technical, so if you're a non-technical person, you should be able to follow all of it and have opinions as to why I'm right or wrong. They're probably wrong, but anyway. And then in part 2, I'm going to explain a bunch of stuff about how semiconductors are made right now, and in part 2, I'm going to look at future technologies. So that's kind of the breakdown. And for some of the sections, especially part 2, I probably have more slides than we have time to go through. So if we run out of time, we'll just skip ahead to part 3. General and philosophical. So if somebody came to you in 1960 and said, hey, in the future, everyone's going to have a computer in their home, and everyone's even going to have a computer in their pocket, and it's going to be thousands of times more powerful than the most powerful computer anywhere in the world today, you should think they were completely bonkers, because the year is 1960, and Gordon Moore didn't come out with his paper until 1965. And that's really the first indication that we have that this exponential trend is going to take off. And the exponential trend, Gordon Moore is this guy. Not Roger Moore, who played James Bond from 1973 to 1985. No, it's Moore's law is named for Gordon Moore. And this is what was in his paper. And this is pretty amazing. He's got 4 data points. Right? And this is on a log 2 graph, so this is, 8, 16, 32, 64. And he looked at that and said, it's just gonna keep going. So, pretty bold. But, look what happened. Okay, now it didn't actually double every year, it slowed down. And in 1975, Gordon Moore came out with a second paper where he said that the doubling time was 2 years rather than 1. So of course, everywhere in the press you see 18 months. Okay? Gordon Moore never said 18 months. But it happens to be the average of the 2 numbers he did give, 12 months and 24 months. I don't know if that's by accident or I don't know where anybody got the 18 months. But I'll have some more accurate numbers a little later. But anyway, you can see, like this is logarithmic over here. It's going 1,000, 10,000, 100,000, and so on. And here's all the processors. Really amazing. This is transistors per unit area, per square millimeter. Pretty similar pattern. Remember, this is on a logarithmic scale, so a straight line means we have an exponential rocket that's taking off. You had a question, Drew?
Oh,
No?
not yet.
Oh, not yet? Okay.
He was practicing.
Okay. Now this really ought to blow your mind. This is one of the most amazing graphs ever. And the thing that's amazing about it is how smooth it is, how close to a straight line it is. What's on this graph is the price of a transistor. At the beginning here, around 1968, it's $1. And then it goes down to a tenth of a dollar, also known as a dime, and then to a hundredth of a dollar, also known as a penny, and then a tenth of a penny, and a hundredth of a penny, and so on and so on. It's an incredibly smooth curve. And think about how many decades this spans, okay? And think about like how many different people and different companies have gone in and out of the semiconductor industry over this span of time, and yet it's maintained this curve. So it couldn't just be like a self-fulfilling prophecy or something like that, right? It's like a law of nature. This is the same graph. But we've also got the number of transistors produced, which goes pretty much mirror image. So as the price goes down, the number of transistors grows insanely fast, insanely much. Okay, what do we have here? Oh, this is hard disk capacity. So hard disks are tiny, and then around the early 90s we get up to a gigabyte. I'm old enough to remember the first gigabyte hard drive, and I was like, a gigabyte? How could anybody ever fill a gigabyte? Well, just start putting photos, music, video on there. But here's, keeps going. This goes up to 2010. Around 2010, I got another chart here. So around 2010, this is looking at price. It kind of slows down. But this isn't a very good chart, but it's the best one I could find. As hard disks taper off, we can see that solid state storage is coming in, taking its place. And that's this purplish blue part in the corner on this chart here. What do we got here? Oh, this is just another demonstration of how solid state storage is taking over where hard disks are leaving off. All right, and this is this is the bit rate. So this is the this has to do with the speed of storage. And so in 2006, Coe and McGee at MIT did a really in-depth study where they tried to figure out the actual speed of Moore's law, and they divided it up into computation, storage, and communication, and they came up with percentage increase per year with error bars. And I decided to, well, first of all, I got rid of the error bars, and I flipped it into a doubling time. So I'm giving you the numbers in terms of doubling times here. So, and remember, this is actually per unit price. So we're not talking about the number of transistors on a chip here. We're talking about how much does it cost to get a given amount of computing power. And the numbers I came up with were 2.19 years for computation, and longer than that for storage, 2.92 years, but still very fast, and 2.42 years for communication. And with communication, you also have bits per cable length, because communication takes into account distance as well as speed. So this is really an economic measure, and this is for 2006. And I think these numbers have slowed down now, but I don't know how much they've slowed down. So things are not going quite that fast right now. But if anybody asks you, like, is Moore's law 18 months, you can say 2.19 years. Okay, so this is a chart that I got from Ray Kurzweil. A lot of you have probably seen it before, or something very similar. So the point that he's trying to make, he goes all the way back into all these different types of computing. And the point that he's trying to make is that when a given type of technology reaches its limit, another type of technology will be invented that can continue the exponential curve growing. So here he's gone back to like electromechanical relays, vacuum tubes, at transistors before the integrated circuit, when people wired together computers by wiring together transistors by hand, right? Remember, before the integrated circuit, that's what people did. The integrated circuit was invented in 1958 by Jack Kilby, but Robert Noyce, who Tom mentioned, was right on his heels, one of the Intel co-founders, along with Gordon Moore. And integrated circuits are really amazing because you can make the entire circuit in one fell swoop. And we're going to be talking a lot about how that is done today. So here's the big question, though. The big question, is when our current method of making semiconductors, which is called photolithography, when that runs out of steam, will the next system be ready to pick up and keep the exponential trend going? And I actually thought years ago that by now it would be really obvious what would be next after silicon and photolithography. And I don't see anything ready to go. So it seems like that's not going to be what's happening. But I'll get into that later on in this talk. Okay. Swanson's law. So there's many other laws that are similar to Moore's law, and this one has to do with photovoltaic cells. As you can see, the cost, this is the module cost, so it doesn't take into account the amount of energy produced. I have another one here that looks at energy. Okay, this isn't the cost of energy, but this is the growth of photovoltaic energy. You can see this is a logarithmic scale. All these are logarithmic scale. You can see we have an exponential trend going up. Okay, genomes. This is kind of a weird one. It's kind of similar to Moore's law up until about 2007, and then it goes even faster. So genome sequencing, for some unknown reason, maybe a biotech person in the audience can explain to us how it's managed to go this fast. Because I don't know, but that's an amazing thing that's been going on.
When was the Human Genome Project completed?
Around 2000,
Okay.
I think.
Probably.
So
2003 maybe?
the question was, when was the Human Genome Project completed? And I think that was around 2000. I'm not sure the exact date.
Okay.
Just
So another thing that people say is like Moore's law is the average sensor cost, so that we'll have the Internet of Things everywhere. And it's kind of asymptoting out. It's not quite going exponentially. Okay, so I tried to put together, for fun, a whole bunch of these kind of laws. Kreider's law, named for Mark Kreider, is magnetic disk storage growing exponentially. Gilder's law is the same thing for communication bandwidth, named for George Gilder. Metcalfe's law, so Robert Metcalfe is the guy who invented Ethernet, and he said the value of a computer network grows as the square of the number of users. So if my network has 10 users and yours has 20, then yours would be 4 times as valuable. All my users are going to leave and join yours, basically, in that scenario. Or you could just hook the two of them together, interconnect the networks, and then you might get an internet, a network of networks. Cooper's law. So Cooper's law has to do with radio spectrum. So the idea is that radio spectrum, as our technology advances, we can increase the amount of communication over the same radio spectrum. He says it doubles every 30 months. I don't know if it's actually 30 months, but that's how it was originally stated. Kumi's law, the energy of computation is halved every year and a half. The energy does go down. We'll see more of that as we get going here. Rock's law. So Arthur Rock was Intel's venture capitalist, and he noticed that the cost of the factories that are used to make semiconductors, which are called fabs, the fabrication plants, that the cost was growing exponentially. And I think this is really interesting because it turns out as you make the transistors smaller and smaller and smaller, it gets more and more difficult. And you can actually quantify how much difficult it gets by looking at how much it costs to do it. You say, how hard is it to manufacture transistors at 10 nanometers? Well, it's almost $10 billion is how hard. That's how hard it is. So semiconductor fabs are pretty close to $10 billion now. I think we're just shy of 10 billion. And Kevin's nodding. Yeah, okay. So Engelbart's law. The intrinsic rate of human performance is exponential. I'm not sure we're getting better exponentially. Doug Engelbart, by the way, is the guy who invented the mouse. Grosh's law. The economic value of computation increases with the square root of the increase in speed. In other words, to do a calculation 10 times as cheaply, you need to do it 100 times as fast. Okay, could be true, I don't know. Gustafson's law. Any sufficiently large problem can be efficiently paralyzed, named for John Gustafson. Now, with things like this, I always wonder, what does sufficiently large mean? What does efficiently mean? What exactly does that mean? I don't know. So here's a fun one, Andy and Bill's law. When a computer chip is released, new software will be released to use up all of its power. So the way I remember hearing this one was, Andy giveth and Bill taketh away. Anybody who was around in the 90s when Bill Gates and Microsoft and Andy Grove at Intel dominated the whole computer industry is going to get that one. So the idea is that, computers keep getting faster, but software keeps getting more bloated. So it all balances out.
We have Bitcoin too. That's using.
Say again?
Or you have things like Bitcoin that are using an enormous amount of processing power.
Right,
Because
Bitcoin.
it was available.
Yeah. Bitcoin is kind of designed to use an enormous amount of processing power. I don't know if that's a typical case. All right. So Moore's law, which sounds like a satire, it's actually not. It's a real person, Calvin Moore. He said an information retrieval system will tend not to be used whenever it is more painful and troublesome for a customer to have the information for than him not to have it. So in other words, if you're doing an unethical job, you could Google it and find that out instantly, but you won't. You don't want to know that. And now this one actually is satire. Eroom's law. Eroom is Moore spelled backwards. Drug discovery becomes slower and more expensive, despite improvements in technology. It's kind of a parallel to Rock's law, if you think about it. All right. And this one's a fun one. Augustine's law. It shows that around the year 2105, which is where this red line and this green line cross, the entire defense budget will buy one tactical aircraft.
Seems like a good business to be in.
So, does anybody know how much an FA-22 Raptor cost? It's insane.
Like 150 million or so.
I thought it was in the billions.
Well, the production cost of one, if you want to make one more,
Okay, so one more is 150 million.
Yeah.
Oh, okay.
And is that Norm Augustine from Lockheed Martin?
I think so. I forget.
Seems like a likely candidate.
Yeah, so 2125 is when the entire GDP of the country will buy one tactical aircraft. That's a fun one. Okay. So, when you ask people why does Moore's law happen, people always say it's a self-fulfilling prophecy. And it kind of seems like it's true because the semiconductor industry has things like the ITRS roadmap. So ITRS stands for International Technology Roadmap for Semiconductors. And it's basically this plan that basically says, okay, we want to go from 130 nanometers to 90 nanometers or whatever. And in order for that to happen, we need to have, these lasers and these optics for the photolithography and, this and this and this. And basically they lay it all out. And then everybody in the industry scrambles to meet those dates. But as you know from my graph of the price and how smooth it is, the price per transistor, I don't think that's the whole story at all. I think that if you think about it, any company would love to be able to jump out like 10 times or 100 times ahead of all the competition and just sweep up the market. And the fact that they can't do this, I think suggests that it can't be done. You need sort of the whole industry to move in lockstep from one semiconductor node to another. And nodes refer to the sizes of the features on the semiconductors. I'll explain more about that in a minute. So if you had like if you do a little thought experiment where you imagine that there's like two separate sets of companies that do all the equipment in the tool chain that you need to make semiconductors, and one of them was going a little faster than the other, then the other would go out of business and we'd just be left with the one. And so I think that's kind of what's happened, is we're just left with one set of companies that sort of, all move in lockstep to smaller and smaller feature sizes. So basically, my answer to why Moore's law happens is it's the speed limit of human innovation. This is my great philosophical insight that I'm going to leave you all with today. So all over the world, there are 7.3 billion humans who are inventing stuff all over the place, and some tiny fraction of those 1 out of 1,000 or whatever, some tiny fraction of those inventions are inventions that increase computing power. And the accumulation of those inventions is what drives Moore's law forward and increases the actual computing power that we have in the world. So, there you have it.
You're done.
All right. Yeah, exactly. Okay, so that's it for part one. Any questions, comments, feedback?
Has anybody, to your knowledge, ever taken a look at all these laws and predicted should they all be true, come to some crescendo where massive breakthroughs come out?
You pretty much mentioned Kurzweil, and have you heard of Kurzweil?
Oh yeah, I've read him
It
for
seems
years.
like that's what you're saying.
Yeah, I'm looking at that place where there's of course, their big word is exponential. But is anybody ever predicted that they all come together in this perfect synergy?
Yeah, he calls it the singularity. Yes.
Yeah, he calls it.
He's
the
predicted
singularity.
it in about 24
40,
years.
right.
Similar to dates that Wayne has mentioned.
Yeah, and I'm wondering, actually, I should have restated, thank you for bringing up Kurzweil, because Kurzweil seems to be the one voice that people listen to. and I'm wondering, is there another voice out there which not necessarily counters, but adds to what Kurzweil predicts?
Well, this is Wayne's talk, but yeah, he's a controversial figure. And
I defer to Larry.
Some people compare him to a religious figure almost, because these exponential laws are real, but predicting where they'll go is speculation. So we're going to look at a completely different future, but not exactly what he's predicting. And so, yeah, he becomes a little bit religious in his
Well,
predictions.
he's a heretic against the traditional
Not to
Western
geeks.
culture.
To geeks, he is their savior.
Actually, there is, so Werner Vinci, I believe, originally coined the term singularity, and he was the one who sort of came up with some of the groundwork, and then Kurzweil extended it, so, and I believe he's still around and talking about stuff. And then also another person who might be interesting to look into is Anders Sandberg. He's written a variety of, shall we say, theoretical engineering papers in which he applies mathematical modeling in order to try and more rigorously attack some of these questions. And one of the papers that he's written is specifically about models of technological evolution and what kinds of deviations or supports from the whole idea of the technological singularity might be out there. So I would encourage you to look into that. Anders Sandberg is his name. He's at the Future Community Institute.
And Eliezer Yukasovich.
Oh yeah,
similar
he's
things
linked
as
as
well.
Kurzweil works for Google, by the way, now for several
yeah.
years in robotics.
Yeah.
And he doesn't go out and say all these crazy things as much now that he's looking for
He
people.
seems to have slowed down. That's
Yeah.
just a feeling. I don't know if that's true.
He's old and cool.
He's kind of like a prophet, like a technology prophet.
So one of the things that I wonder about is for trends that are not information processing. So for information processing, like you can imagine, this is a simple idea to sort of gain an intuition as to how information processing can double like this. Is imagine you were doing computations on a desktop with piles of sand. So a pile of sand means 1 and no pile of sand means 0, and you can like build up and tear down piles of sands to do all your computation. Well, you could decide the next year that you're going to cut them all in half and use half as much sand, and you still have a pile of sand. So that's how you can double and double and double. But you can also kind of see in this little illustration why at some point you're going to run into trouble, because at some point you're going to just have 1 grain of sand or only a very small number of grains of sand, and then the doubling is not going to work anymore. And that actually applies to semiconductors. You notice, though, that for some of these exponential trends, like photovoltaic, it's not really information processing. So I don't know how long it's going to be able to continue an exponential trend. It's kind of piggybacking on the semiconductor manufacturing, and that explains part of it, but I don't know. So, and for the next part of the talk here, I'm really just going to focus on computation. So I'm going to kind of set all those other exponential trends aside. But I thought it would be fun to look at them because people often say, oh, this is like Moore's law, or this is part of Moore's law. So figured you'd all want to know that all those ideas are out there. So let's dig into photolithography, shall we? So here we have Robert Dennard, who, as you can see, looks very happy about what he's discovered. And what did he discover? He discovered the MOSFET scaling rules. So MOSFET are the semiconductor transistors that we make on silicon. So he discovered that every time you make your dimension smaller by some factor that he called lambda, you get improvements in all these other things. Especially down here, so we have doping, concentration, voltage, current, capacitance. Here we have delay time, that's a fun one, so your chips get faster and the power goes down, but the power density stays the same. So you use the same amount of power, but you get a lot more computation done, and you get it done a lot faster. And everything gets better. That's why he's so happy. It's like, everything gets better, yeah. Okay, now, you may have noticed that around 2005 or so, computer chips stopped getting faster. You're probably wondering, what's with that? Why are we not getting our improvements in delay time? We're continuing to make the transistors smaller. Everything should be getting faster. And it turns out the answer to that question is actually temperature, believe it or not. It's partly voltage too, because the thing is, I got another slide on this. When you have a chip at room temperature, temperature means that your atoms are jiggling around. And in order to overcome the jiggling and do meaningful computation, you need to have a certain voltage to overcome the thermal noise. That's this equation here. And basically, T is the temperature on an absolute scale. Don't be scared by this. I know equations are scary, but these are all constants, and it just relates temperature to voltage. So if you have room temperature, you can't go below a certain voltage, and you have leakage problems and various things, and you can't continue to increase your speed. And that's why our clock speed got stuck around 2005. Now, if we wanted to, we could make the chips faster by, using liquid nitrogen to cool them and stuff like that. But there's a problem, which is that you have to actually design the chips differently. And the reason you have to do that is because your doping concentration also matters, right? So there's other things that matter, and even the geometry. The physicists have told me that the three-dimensional geometry that we do with the FinFETs, I'm going to have a picture in a minute so you'll know what I'm talking about. But people said that actually doesn't work at super cold temperatures. You have to have different geometry. So there's a whole bunch of design changes that have to change when you design the chips to operate at super cold temperatures. And maybe someday, Google or some company with gigantic data centers will create a large enough economy of scale that the semiconductor industry might produce chips that work that way. But as things are right now, we make the chips to work at room temperature, and so our clocks are stuck. Okay, I love this picture. So these little waves that you see here, these are from light waves, okay? This picture is so zoomed in that we can actually see the remnants of light waves. And you're probably wondering, how is this photograph taken? And the answer is, this is not a photograph. Photographs are made with photons. This was made with electrons. This is an electron microscope picture. And as you might guess from the little arrow that says standing waves, what's going on here is that you have light waves coming down and bouncing off the bottom and going back up and exactly where they came down, and that's called a standing wave. And in the semiconductor industry, they have various stuff that they can do to the silicon surface to reduce that. By the way, the wavelength here is either, I don't know what it is, but it's probably either 248 or 193 nanometers. And the chips that we're making now, the feature sizes are smaller than that. So this is actually a lot bigger than current chips. And of course I said nanometers, and you guys are probably wondering, nanometers, how big is a nanometer? So, a note on small. Computer chips are small. Red light has a wavelength of 700 nanometers approximately, and blue light is about 400. And that's the smallest wavelengths that our eyes can see are about 400 nanometers. And what this means is that anything that's smaller than 400 nanometers is so small that you can't see it even if you have the most powerful microscope ever. The wavelengths of light are simply too big to see the thing that you want to see. So we fat-fingered apes have somehow managed to build things that are so small we can't even see them. So how do we do that? It's complicated. So we have a retrovirus here, 70 nanometers, and he says patterns printed with lithography to make transistors are as small as 25 nanometers today. Today is 2013. Okay, we're down to 10 nanometers now. How nuts is that? So small you wouldn't believe how small. All right. Okay. So this is the sort of main picture for this section. The sort of overview of the process. We go from wafers. We coat them with photoresist. We pre-bake them. We expose them to light. The PEB stands for post-exposure bake. Develop is where we actually deposit material or remove material, which is called deposition or etching. Metrology, I'm not going to talk much about metrology, but it's very important because this is where you verify that what you did was correct. Right? So if you make a chip and it doesn't work, something's wrong and you need to fix it. All right. Oh, I got a video here about the sand. And I'm just going to skip around here. But this is a little video that Intel made years ago. You take a bunch of sand. Let's get forward here. You melt it. So sand is silicon oxide. And you turn it into this ingot thing. And then you chop out wafers from it. And you polish them so they're nice and perfect. And the crystal, the surface of the crystal is like atomically precise. It's really amazing that we can do that these days. And then you go and you expose them to light to make your chips. So that's kind of the start of the whole process. And it's been that way for decades. You put the photoresist on by spin coating it. If you have the right viscosity, you can just blob it in the middle and spin it, and it'll make a nice even coat, believe it or not. The photomask. So what we're going to do is we're going to shine light through a mask onto the silicon wafer, and the photoresist, which is on the wafer, is going to react to the light. And that is what is going to enable us to make a pattern on the surface of the silicon. I'll have more to say about the photomask later, but that'll do for now. The light source. It turns out it's not ordinary light. It's not the light in your living room. It's something known as an excimer laser. Excimer is short for excited dimer. All the semiconductors these days are made with the argon fluoride 190 nanometer wavelength. So remember, the highest wavelength that your eyes can see is around 400 nanometers. So this is much smaller. So this is in the ultraviolet. So we're already in the ultraviolet. So light that's too small for your eyes to see. And it's also pulsed. So they don't shine it continuously, they emit these pulses. Here's some pictures of what these tools look like from ASML and Nikon. I wish they had like a human in the picture, because these machines are actually really large. You can't really tell from these photos. Diffraction. Okay, so I thought it would be fun to delve into this issue of diffraction a little bit, because this is an area where our intuitions as to how things work from our experience at the macro scale doesn't actually apply at these nanoscales. In particular, if you have an edge, like say this is a pattern on your mask, you have an edge here, and you're shining light through it, you would think that the light would make the same edge on the silicon surface, but it doesn't, because light diffracts around that edge. And that is a huge problem as you try to make things smaller and smaller. So here's a picture. So with no edges, you get this nice wavefront. When you have edges, things radiate outward around the corners, and you get diffraction. And the smaller your feature size, the bigger the problem. So you want to let light through here. If you have a big opening in your mask, you get something that corresponds pretty much to the pattern on your mask. Not perfectly, but if it's really small, then it's nothing like it. Okay, here's my little animation. Let's bring that up. Fun little animation here. Okay, so I'll just stop it there. So you can see, so the large slit is over here, the small slit is over here, and this is the single slit experiment. As Trent so famously said. Okay, so if you have a large slit, the pattern that you get on the wafer is kind of more similar to your slit, which is the pattern on your mask, than if it's really small. It gets really hard to see.
Is that behavior consistent or is it arbitrary?
Well, it's consistent based on the wavelength of the light. So we're talking about when you have the size of a slit here that's very similar to the wavelength of the light. I'm not sure I understood the question correctly.
So I guess I'm wondering, is they're employing diffraction, do they know exactly what result they're going to get as a result of this?
Yes, because of Fourier transforms. Because you do. So the way that you compute this, you may be familiar with Fourier transforms for like changing the pitch of audio and things like that, where you have like a time dimension and I guess it would be like an amplitude dimension. But you also use Fourier transforms in more dimensions. You have like 2 dimensions for the x and y of your mask, and then a time dimension, and you can compute. You can compute all of the diffraction. You can compute exactly how the light diffracts and what you're going to see. And in fact, I have a picture in here of how you can change the mask to compensate for that.
Well, they have to be able to change the mask to compensate for it to get reliable, repeatable results, right?
It's
Well,
one
they
of
know
the
exactly
it's one
what
of the
to do.
things they do. They do a lot of clever things,
Okay.
and I'm going to show you some of them. So let's get back to the slides.
That slide you showed with the ridges and the transistor, that was a result of diffraction. We can call that the electron micrograph of the chip.
No, that was standing waves.
From what?
Hmm?
From what?
He's asking about this.
No, I know.
Did that not come from the?
But
This
where,
picture
where
here.
do they get the standing
These
waves?
are
'Cause it's
standing
not a
waves.
diffraction pattern.
Is that just random?
No, it's from the wavelength of light that's coming through. Light at a certain wavelength comes in, bounces off the silicon wafer, and goes back up in exactly in a way that retraces its steps. And that's a problem. They try to prevent that in
So
silicon
did they take
manufacturing.
that electron picture while there was light on the chip?
Probably not. It was probably made afterward. All right. So So, oh yeah, Fourier transforms. I told you about that. So we've got number of diffraction orders. So number of diffraction orders has to do with the size of the lens and how much of the light it manages to collect. So if you think about wavelengths of light, if you have n equals 1, that's just the effect of the main wavelength. But then you have another wavelength that goes out and comes back in through the lens. I should have had a picture of the lens in here. You have light that goes out and comes back through the lens. And when you have one of those on each side, then you have n equals 3. And you can see like the bigger your lens is and the more light it captures, the more number of diffraction orders it captures, and the closer you get to matching your mask pattern. So n equals 9 is this green pattern here, which is much closer to what you want than any of the others. The red one is just kind of like this bell curve thing.
So the n is like a number of inflection points, right? That's what it's like.
Uh,
Or is that something else? On that graph.
I don't know if inflection points is the right term.
Well, I'm not sure.
Yeah. But you have a lens, and if the lens, like you have light coming straight through, that's your first order, and then you have light that goes at an angle and lands at the same spot on the other end, and it comes and interferes with each other, so it can like the peaks can add up, or the valleys can cancel out when they get to the other end.
Just to check that last graph, was that related to was that like the actual physical manifestation of the light, or was that related to the Fourier series? Because it looks kind of like a Fourier
I think this
series
is computed.
Yeah, of a unit step function or something.
Yeah. Yeah, I think this is a theoretical computation of what you would get if you had exactly these diffraction orders.
Gotcha.
Oh, I skipped one here. So another clever technique they came up with is to take the light source and move it off center. And if you move it off center at the right angle, then what happens is you get rid of the one in the center, and you see how these are all odd numbers, you get all even numbers. And you're actually able to double the resolution that you get on the other end. In order to give you guys some intuition as to how this works, I put in a couple pictures here that show how if your light source is on center, you have wavefronts that are all lined up like this, but they go at an angle if you move your light source off center. And they also, because the light goes through the lens in multiple paths when you have it off center like this, you increase the odds that the peaks will add up, and the peaks and valleys will add up at the particular spot on the silicon where you want your feature to be. Okay, another thing they do is they change the shape of the light source. I'm not really sure how that improves the manufacturing, but they do it, so it must. This is what I was telling you about how they actually change the shape of the mask. So they know if they have the mask exactly like the pattern they want, when you shine the light through it, you're going to get all these diffraction problems. So why not just change the pattern to this funky thing? And then when you shine the light through it, you'll get this. And they do all those Fourier transforms to figure out this. So this is what your mask actually looks like. It looks something like this. It has these, serifs and anti-serifs on the corners and weird stuff like that. Another trick, phase shifting. So if you have some slits in your mask, the valley in between them, the light intensity is not 0. But you want it to be 0, so what you can do is you can put some material on this one, and the speed of light in this material is different from air, so you actually shift the phase of the light here, and you get 0 light intensity in the middle. That's another clever trick they do. Okay, so I thought I'd include all these things to give you guys a flavor of just the insane complexity that people deal with when you manufacture something at nanometer scale and the crazy solutions that people have come up with to keep Moore's law going. Okay, so numerical aperture, I was talking about earlier, your ability to capture stuff with the lens. It turns out that beyond a certain point, you have to immerse in water. Okay. Why does that work? Well, water has a refractive index of this number, 1.346, and you can see this when you like stick a straw in water and stuff. And I don't understand the details of it, but if you immerse the chips in water when you're doing the exposure, it turns out that you can redesign the whole optical system to give it a higher numerical aperture. Maybe someone here who's a camera geek can figure out how that works. Okay, so the next thing here is the photoresist. I'm not going to go into photoresist too much. Photoresist is a whole black art of chemistry. It used to be, when they first started making chips, that the photoresist would change solubility directly in response to light. So you shine light in certain places, the solubility changes, you wash it off in just those places, and now you have a pattern on your chip where the photoresist is left. The way they do it now is the light will interact with the photoresist to generate an acid, and the solubility change happens afterwards in the post-exposure bake, which you'll remember is, I'm getting kind of far away from my, I passed it here. So you do your exposure, you do your post-exposure bake, and a whole lot of chemical black magic with your photoresist is going to happen in that stage there. Let's see where I was here. Okay, so the next stage after the post-exposure bake was development, and this is where you actually either deposit material or you remove material. So if you're adding material, that's called deposition. There's a whole boatload of deposition techniques that are used in the industry. Physical vapor deposition, chemical vapor deposition, electrochemical deposition. So with chemical vapor deposition, it's different from just vapor deposition, physical vapor deposition, because with just physical vapor deposition, you have a vapor that deposits material basically everywhere. But when you have chemical vapor deposition, you need a chemical reaction on the surface in order to get the deposition to happen. And this is what's used most commonly in the industry. And then they also do some clever stuff for the metal, because you need metal for the interconnects, and I'll say more about that later. So when you're removing material, that's called etching, and there's a boatload of etching techniques in the industry. I did put in a slide here about reactive ion etching. So the idea here is that you have a plasma and you have ions, which is some sort of heavy material that you use like a magnetic field to redirect it around, and then you also require a chemical reaction usually on the surface of the silicon wafer for the etching to actually happen, for the ion strikes to actually remove the material. And this word anisotropy here. So what that refers to is a lot of times when you're etching, it can be hard to etch things so that it's perfectly straight. You can have things etched at an angle, so there's like overhang, right? So you want to have an etching system that doesn't have problems like that. Okay, double patterning. So this is another one of the clever techniques that the industry has come up with to basically double the resolution of the feature size that they can manufacture on computer chips. And there's many different double patterning techniques. I'm using just one here for illustration. The idea is that you leave a pattern in your photoresist like this. You fill up the space with some material, you etch it away, but not completely, so you're left with these little pieces. And then you remove you strip away your first pattern, and then you etch using your second pattern at twice the resolution. And here's some electron microscope pictures of what that looks like. Okay, so I haven't said anything about how the masks are made. They're basically made with electron guns. So they're etched with electrons. It's kind of, if you think about like how an old CRT works, by shooting electrons and using magnetic fields to control them. It's kind of the same idea. So you have something up here that fires electrons. You have a bunch of stuff that controls its movement, that focuses it, and then you have your mask on the bottom. And the mask, remember, is not silicon. It's I actually think it's like some kind of molybdenum material. If you're wondering why, because electrons are smaller than photons, if you're wondering why they can't just etch the chips directly with electrons, the answer is that you couldn't make enough of them that way because it's a really slow process. You basically have scan lines, and because the circuits are so complicated, you have a gazillion scan lines, and it takes a really long time to etch it. It actually takes a couple days, I think, to etch a mask. So you etch a mask, and then you use the mask to crank out billions of chips with photolithography. So if you think about what the semiconductor industry does, they basically manufacture billions and billions and billions of transistors in insanely massive amounts, billions of chips in all our cell phones. And you need the optical photolithography to do that. Okay. Oh, so I haven't said anything about what you actually etch on the chips, what you actually do. So this is all about how you make a circuit on the chip, but what do you actually do? What do you actually put in there? And the main thing that you do is you put in things called dopants, which change the electrical properties of the silicon itself, and you add to that material for the gates for the transistors and material for the wiring to wire it all together. So what we're talking about here is the dopants, and we have, for example, boron and phosphorus, which are in the columns next to silicon, which is number 14 there. And so what the dopants do is they increase or decrease the number of free electrons that can move around and do stuff in your circuit. If you take away electrons, in the industry, we think of this as like creating holes that electrons can go into. So you have positive holes in your p-type and negatively charged electrons in your n-type. The thing to remember here is you're not actually changing the charge of the silicon, but you are changing the mobility of the electrons. Okay, so now when you put the two next to each other, you get what's called a depletion region, where some of the electrons go to the other side and some of the holes go to the other side, and everything kind of balances out in the middle. And what this does is it creates a barrier where current doesn't want to flow. And when you hook two of these junctions up, so we have an N region, a P region, and an N region, then the current doesn't want to go from the N regions through the P regions unless you put a voltage on the gate. And that is the whole magic. Because you put a voltage on the gate and ba-boom. And this is how a transistor acts as an electrical switch. So if you think of a mechanical switch like a light switch, it basically opens and closes a circuit. Transistor does the same thing, but it does it all electrically, all using a voltage. Now, if all you have is one transistor, that's not very useful. But if you have a lot of them, if you have billions of them, you can do really interesting things. you can combine them to get logic gates. And this is a NAND gate. So it takes the NAND of A and B. NAND means not and. So the output is going to be, it's going to be the AND of A and B inverted. And so this is what actually gets etched on the chip. If you do that, the blue and the green are the metal conductors. Well, blue is metal. Green is polysilicate, which is a way of making wires that are very short distances. It doesn't work for long distances, which is where you need your metal, which nowadays is usually copper. So the red is your N regions, the P is your, the yellow is your P region, and it's kind of easier to see what's going on in the circuit diagram. But that's basically how you create it on the circuit, and I've got some circuit diagrams here for an AND gate. So, so if you have A and B, then your output is going to be, you're going to have a voltage on your output if you have voltage on A and B. So you think of it as being binary. You think of it as being one here, then you get one here. Otherwise, you get the 0 for the output. Here's an OR gate. So you can see you can make all these things out of transistors. So your output here will be 1 if you have a 1 on either A or B going in. And this is what it typically looks like in an engineer's circuit diagram. And here's our little truth table that shows this is an AND gate, so if we have a 1 on both A and B, or inputs, and we have 1 on your output. And in real circuits, you can have more than 2 inputs. You can have lots of inputs. But 2 is sufficient to get the point across. This is all the logic gates. NOT gates, there is such a thing as a NOT gate, but NOTs are usually combined with the logic gates to reduce the number of transistors. So we have AND and NAND, OR and NOR, XOR and XNOR. XOR is exclusive OR, and it basically means you have one or the other, but not both. So if you have A and B, then this comes out 0. And it turns out that with these logic gates, you can make a computer that can compute, well, not literally anything. You know, I guess that goes back to whether P is NP.
Apparently it is.
You can compute. You can compute basically anything. In theory, you could compute anything if you had infinite time, but you can make all your arithmetic operations, addition, subtraction, multiplication, division, and so forth, using just these logic gates. Oh, so I got a picture here of the wiring. So we think of circuits as being two-dimensional, but actually there's a lot going on in the third dimension, and that's where all the interconnects are. So we have the transistors on the silicon, on the surface, and then for wires that need to go very short distances, we use this bottom layer where we have these very small, short distance copper interconnects. And then for the stuff that needs to go way across the chip, we have these fatter wires that are higher up that carry information from one part of the chip to some distant part of the chip. So it does actually use all 3 dimensions. All right, so that's the end of part 2. I managed to blitz through it. So, questions, comments, suggestions?
Fact checking genome was 2003. Incremental unit cost on F-35s is 94.6 million. So they're a bargain, but the rumor is that we're going to be able to get Putin to make them for half that price in Russia. And I did have a question on the cooling. Is that not linear? Why are we stuck? You seem to go to really, really cold stuff from room temperature to really, really cold stuff. Is there nothing in between?
I don't know. Maybe there could be.
I take that as a yes.
The idea though is that you need to go back to my Dennard scaling picture here. The idea here is that in order to keep your Dennard scaling in step, you need to be able to decrease your voltage. Every time you make your transistor smaller, you need to drop your voltage. Well, it turns out at a certain point you need a certain voltage to overcome the thermal energy, to overcome thermal noise. So that's where that comes from.
But if you went to just like 40 below, that's not good against you.
Well, I'm guessing probably not, because the temperature is on the absolute scale. So it's on the scale that goes from absolute to 0. So we can drop the temperature, something that feels to us like a lot. But, you know, room temperature is like 270 on the Kelvin scale. So if we go from 270 to 230, it's like we haven't really gone that far, but we've made it something that to us seems insanely cold. That's kind of my thinking on that. If any of the physicists want to weigh in on that.
So I have a question about the 25 millivolts. If you go to a higher voltage, does it arc across from one?
I think what happens with the higher voltage is you just get leakage.
Yeah.
You just get a lot of current leakage.
I think there's something called latch up where it's almost like a short circuit.
That says, yeah,
Yeah.
shorts out. Because, you know, like, I think an inch, 25,000 volts takes to cross an inch, but if you're going to micron, well, it doesn't take much.
I have a background in metrology, but it goes back about 15 years. So
Okay.
Optical metrology back then with circuit manufacturers and the like, when we weren't dealing in single-digit nano sizes. I'm curious about the dimensional verification of the masks. What kind of resolution do we have in terms of optical measurement today to be able to verify masks that are of a size to create features of the size we're talking about? They must have done so much development in the last 15 years in terms of the resolution and accuracy of dimensional metrology optically based compared to 15 years ago. I can't even relate to it.
I don't know that it's optical.
Is it all electron microscope? To get to that resolution?
I know they've come up with a lot of clever techniques that they use to repair the masks when things go wrong, because it's cheaper to try to repair problems than to make a whole new mask.
Is there a wear factor on the masks of any kind, or do they stay dimensionally the same for their life?
That's a good question. I don't know. I would think there would be somewhere.
I would
on
think
them.
of some kind.
Yeah.
I think it's amazing that people can make these machines, that humans make tools like this. Just look back 100 years ago to now, it's just incredible.
Yeah. This is really all started in the late 50s with Jack Kilby and Robert Noyce and those guys.
There's an expression in the semiconductor business that they use the current generation of computers to design the next one. So some of this technology is built using what you created. You couldn't have these enormous fabs without super computers helping us build them. Some of what's going on is we create a computer, and that computer helps us build the next computer, so to speak.
It's another driver for Moore's laws, what it sounds like. You've got to have some foundation
Yeah, I
first
think
to make
it's
the next.
it's like a hidden side. It's like a support system alongside the
Yeah.
technology.
Right.
I wonder how
Yeah.
often the fabs have to be retooled for the new technology and the new chips that are being made.
Okay, so first responding to his comment, and I'll get to yours in a sec. There's a whole field of software called electronic design automation software, EDA software, which is made by companies like Synoptics. And they do an insane amount of computing power that goes into designing the circuits and working out the physics of a lot of this stuff. So it is really true that the computing power that we have now is used to produce the next generation. In regard to your question about retooling the fabs, they pretty much have to be completely retooled with each successive generation of semiconductor equipment. There are some things like lasers and stuff that you can keep using, but there's a whole lot that just has to be just redone for the whole process, for the whole thing. Capital investment is huge.
Is there like a secondary market in old photolithography equipment?
Oh, certainly. There's people that make chips, at much larger sizes than the cutting edge that they use for like embedded systems and stuff.
And they buy like IBM's old equipment.
Sure. Yeah. People still make like Z80 chips, and they make them at larger feature sizes, and they put them in I don't know, microwave ovens or something. I don't know what the hell they put them in. There's computer chips in everything now, and not everything needs to be cutting edge. So
And it's cheaper to build.
absolutely.
There you go. Gotcha.
Yeah, it's cheaper. The old stuff is cheaper.
Yep.
Speaking of fabs, you had that rule that the cost almost doubles or is going up exponentially for fabs, but
Yeah.
wait a minute, that cost can't climb much higher, and I think if you graphed the cost of fabs over time, it might be approaching a ceiling, because $10 billion per fab. Okay, you can't just say, here's my $20 million or $1 billion fab. So that's a factor that may be impacting Moore's law at this point. Is
So the cap might be just that it's not worth the capital investment.
who's going to make a $20 billion fab? I believe that's a ceiling that is right now being reached, and they'll keep building fabs, but they're not going to be twice as expensive, probably. So.
Yeah, so Gordon Moore actually thought that economics would have caused a limit around, I think it was like 2005 or 2010 or so. But we've continued past that, and it looks like we're gonna continue until we reach actual physical limits. So.
And the fab is a physical limit, by the way. We're focused on this chip, right? But
Yeah.
okay, if you have, a Tesla or Elon Musk is trying to build a gigafactory, right? Well, I don't think you can build one bigger than that, and he's probably not going to build chips with it. So it might be he's making the largest factories that will exist in the future. Maybe fabs won't get bigger, possibly. Chip fabs.
They don't have to get bigger, just more expensive.
But can they afford double what the current fab cost is, which is like Intel can barely buy a new fab, at this point. Intel is not doubling, so that's a limit that is showing up.
That's a fair point. So we don't know how high the cost of a chip fab can go before it becomes just completely uneconomical. The world economy can't support it going any higher. Okay, so should we go on to part 3, the future?
Yes.
All right, the future. Okay, so the first thing to talk about is extreme ultraviolet. So, as I mentioned before, the argon fluoride excimer lasers are 193 nanometers, and the plan with extreme ultraviolet, which a few companies say they've actually gotten working at this point. Hasn't TSMC or Samsung, so they've got EUV working? I'm trying to remember. I should know this. They don't have commercial products using it, but there's some companies that have said they've manufactured some chips using it. But anyway, what is extreme ultraviolet all about? Well, the idea is to jump all the way down to 13.5 nanometers. So, and if you guys have been following me through all this, that should seem pretty extreme, justifying the extreme part. why jump all the way from 193 to 13.5? And the reason is air, believe it or not, becomes opaque to light in the region in between. So we could suck all the air out and make chips in a vacuum, or we could just skip over all those wavelengths and jump to something really small. It turns out there are some problems though, and one of them is that you have to do all reflective optics, which means you can't do lenses, you have to do mirrors. Everything has to be mirrors. I'll have a picture of that in a minute. 96% of your light gets lost in all your mirrors, so your light source has to be very bright. And one of the biggest problems in the industry, I don't know how they've gotten around this and gotten EUV working, but there have been huge problems getting a light source that's bright enough. Mirrors have to be made out of molybdenum polysilicate to reflect the material. So the material that's used for the normal lenses is it's some sort of polysilicate material. The light source, they use tin for the light source. So SnH4, Sn is tin, and you use a carbon dioxide laser to energize it. And this causes a problem because you get tin and hydrocarbons all over everything. And nobody has solved this problem. Apparently, you just have to let the light source degrade and replace it periodically with a new one. And you have to have a membrane to separate your light source from everything else so you don't get tin and hydrocarbons contaminating everything. Another problem you have is that the EUV photons are so energetic that they ionize material when they come in contact with it. So the traditional photoresists will not work with EUV light. They have to work in a fundamentally different way, and I know you're all going to ask, how do they work, Wayne? I don't know. That's like trade secret or something. People, but like I say, photoresist is chemistry black magic. So there are people who figured that out. Here's a picture of the mirrors. You have your light source, boom, 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 boom. Your wafer's way over here. That's what you have to do to focus it. You put in your tin, you got your plasma here, got your CO2 laser. Try to collect your tin down here. Kind of messy. Okay, so this picture, what we have over here is a jillion various things that need to be done in order to make chips at a given feature size, and the feature sizes are 10, 7, 5, so 5 nanometers, 7 nanometers is here, 10 is the current size, 7, then 5, then 3, then 2.1. They're hoping to do 2.1 in 2027, 1.5, and 10. And so what the colors mean is everything that's in yellow is something that we think we know how to do, but it requires EUV. It requires extreme ultraviolet in order to do it. So the yellow stuff should be doable with EUV. The red stuff, though, here, we have no idea how to do that. So if you know the solutions to any of the stuff that's in red on this picture, there is a job with your name on it in the semiconductor industry. Okay, the next idea for moving Moore's law into the future, gate-all-around transistors. So a standard transistor has the gate on top of the silicon, and around 2012, Intel started making these FinFET transistors, and by fin they literally mean fin. See, it's got a fin that sticks out here. And the gate wraps around the source and the drain, the ends of the transistor. The gate wraps all the way around. And so but it doesn't go all the way around. It just does 3 sides. So the idea with gate-all-around transistors is to go all the way around, to do all 4 sides. As I've got a picture of that here. So you go all the way around. Okay, another idea for keeping Moore's law going. Alternate materials, one of which is to use, instead of straight silicon, you use a silicon germanium alloy. They say silicon germanium transports holes better than silicon, and the silicon lattice doesn't match up with silicon, so you can't combine them with silicon. You can't combine silicon germanium with silicon very well. Nonetheless, Samsung says that they have, in the lab, not commercially, made this work. Moving on with alternate materials, this is what I think the industry is most likely to do, is to use indium gallium arsenide. Now, the interesting thing about indium gallium arsenide is when you make transistors with indium gallium arsenide instead of silicon, the transistors work in a different way. They're what's called tunneling field effect transistors. So they use the quantum tunneling to make the transistor work. So with a normal transistor, as the transistor gets smaller and smaller and smaller, the tendency of electrons to do what's called tunneling becomes more and more of a problem. And what tunneling is because of like Heisenberg uncertainty and stuff like that, electrons can just disappear in one place and appear someplace close by. And if they do that on one side of a transistor and just magically appear on the other side, that's a bit of a problem. You don't want them to do that. So this becomes more and more of a problem as the transistors get closer and closer to the size of individual atoms and individual electrons and so forth. Somehow, and I don't know how, people have figured out how to take advantage of this tunneling effect and use that to make the transistor switch. And that works at very small scales. And exactly how indium gallium arsenide enables you to do that, I don't know. It's some clever chemistry for sure. Did I cover everything on there? Oh, here's an important thing to know. You get twice the performance. So Intel demonstrated that 80 nanometer indium gallium arsenide gives you the same performance as 40 nanometer silicon. So the indium gallium arsenide computer is basically the equivalent of silicon at half the linear size, which is amazing. Okay, so hopefully at this point you guys can understand this otherwise cryptic graphic. So here's where we are now, 22 nanometers, 14 nanometers. You have your regular silicon FinFET with your gate wrapped around the fin in the third dimension. Around 10 nanometers and 7 nanometers, we can use some exotic materials like silicon germanium, which I talked about. And then as we go from there to 5 and 3 nanometers, we can do the silicon germanium gate all around. The 3-5 FinFET. So 3-5 just means you're talking, okay, indium gallium arsenide. Indium gallium and arsenide come from group 3, the group 3 and group 5 columns in the periodic table. That's where the 3 and the 5 come from. So there's a picture of that. And Applied Materials, which is the people who made this slide, they think that we're going to want to do the tunneling field effect transistors vertically like this. So that's an idea, and we'll see if that happens. Yeah.
In the newer terms of voltage on the block, are they going to be able to use a lower voltage?
Pardon me?
Are they going to be able to use a lower voltage?
That's a good question. I don't know. When you change the material, you definitely change the band gap, which is the gap between the electrons that stay fixed in the material and the ones that can float around. That probably changes, and so I would guess it would change the voltage that you would need. Beyond that, I don't know. I don't know specifically. So, good question. Anybody will care to comment on that?
That's part of Dennard scaling to decrease voltage.
Yes, but the scaling in the slide I showed you with Dendron scaling, I think he's assuming it's all silicon, right?
So anyway, that's the goal. They would
So-
like to decrease voltage because
Well, I assume if you switch to a different material, you're going to have to decrease the voltage with that material, but there may be it may be different for the other material as compared to silicon. I would guess so, just because the electrical properties are going to be different when you switch materials.
This one down here is relying on a completely different physical effect, a vertical two-foot
Mm-hmm.
quantum tunnels.
Yeah.
I don't know how that affects it, but it probably does.
Yeah, that's a good point.
So how available is this new material, the gallium nitride? Where's all this coming from? Is it
The only thing I know is that, going back to there, Samsung claims that they have made 7mm chips with it, or 7 nanometer. Excuse me. That's a big difference.
That's not
A
impressive
factor of
at
a million. 7 nanometer chips. They're not commercially available, and that's all I've heard.
well, no, but the material itself, I mean, you started off with a desert of sand, so silicon is
Yeah.
cheap, literally. But
Yeah.
gallium nitride, where's this
gallium,
stuff?
Germanium, yeah, they're all more expensive materials, and that means that your chips will cost more.
Well,
So,
is it available from everywhere, or is it just in
Geopolitical question.
yeah, yeah. Does anyone know
That's a good question.
where germanium comes from and how much it costs?
I've heard about it being used in photovoltaic cells in more advanced ones recently, but
Okay.
I haven't heard of it being used commercially yet, just that it's starting to be used.
there's something used in cell phones. It's mined in Africa, and I can't remember the name of it, but it's politically sensitive because they use slave miners or something. So that shows up in the cell phone industry already, and wouldn't be surprised if there are political situations with where you get your exotic materials here, because there was it Indian, yeah,
It sounds.
something
That's. I
like
think
that.
that one sounds pretty right.
Yeah, and so these might come from exotic places, and there might be politics involved.
Coltan is, I think, the mineral.
Well, that could have been it too,
Yeah,
yeah.
you know, they're using blockchain technology now to track the mining to make it more fair for
We should have some idea on that, Wayne, because germanium was back in the Paleolithic era of transistors. Was
The first
primary
transistor,
material
yep.
used, and they moved to silicon for sourcing. But we should have some pretty good idea on the availability of this.
I'm sure it's a Google search away.
As are all.
That knowledge. Maybe somebody can do that well. I'm gonna go on here. Okay. You know what? I need to tell. Where the heck is Flux here? I need to tell it to show. Yeah. I can't even see it because it's like shrunk my. Oh wow. Crap. I'm trying to get Flux to shut off so it doesn't make my screen yellow. And normally it appears on the bar across the top here, but it's scrunched it up so it's disappeared.
Because the sun went down, right?
Yeah.
Oh, great. Yeah.
Yeah, because the sun went down.
Yes.
I should have thought to turn it off before hooking up the projector. Oh,
Fade to black.
shoot.
We can go to settings.
Yeah, I think so. System preferences. That's it right there.
Yeah, I was thinking it was in applications. This must be incredibly boring for you.
All right, well,
Well, you don't know. You can leave it this way. I won't have any trouble sleeping tonight.
Shoot.
Our eyes will get used to it.
Yeah, I think we'll get used to it.
I guess we'll just have to
It's okay.
roll with it.
We are also fairly close to the end.
So let's see if we can just brighten it a little. Okay. So I wanted to talk about a bunch of stuff that people always say will keep Moore's law going, but it seems to me like probably not. Directed self-assembly, junctionless nanowire transistors, graphene and carbon nanotube transistors, spintronics, silicon photonics, and MEM resistors. So directed self-assembly, I haven't heard anything since 2013. The idea is that you could make molecules like carbon nanotubes or something, throw them together, and they would just magically know how to assemble themselves.
Into a NAND gate.
What's that?
Into a NAND gate.
Into a NAND gate, exactly. I haven't heard of progress on that. So graphene, the thing about graphene is, what physicists tell me is that the band gap isn't large enough to make transistors. But the interesting thing about it is, for some reason, when you roll them up into carbon nanotubes, you actually can make transistors, because the carbon nanotubes can have different electrical properties depending on the angle at which you roll them, which is called the chirality. I have a picture of this. So here's your hexagonal, so your graphene is hexagonal carbon rings, and you roll them up into graphene, and there's more than one way that you can roll them up. So if you look at this carbon nanotube, you'll see that, you know, like you have these horizontal bonds going up this way, but on this one you don't, right? You have the vertical ones. You don't have any horizontal ones. And then here's another angle. So depending on the angle that you roll up the carbon nanotube, you actually get different electrical properties, and that's what...
Spiral tilted? I can't tell.
Yeah,
the
it
difference.
is,
It's
yeah.
tilted and it spirals this way.
Yeah.
Yeah, it just looks very similar to
Yeah, so you can see like this one goes this way, this one goes this way, and this one goes that
It's
way.
almost like the armchair, but slightly.
So they're like
that,
30-degree rotations. Let's see. Did I get everything here? Yeah, they've made transistors with 5 nanometer gates, pretty small, lower voltage, higher current than silicon transistors. Lots of stuff turns out to work better than silicon transistors, although it does have a few problems, like it degrades when exposed to oxygen. It's also more sensitive to temperature changes and electrical fields in the environment than silicon is, so that's a problem. And this is the big problem, which is nobody has figured out how to mass manufacture them. This is the problem for all the alternative technologies, because what the silicon industry does is it manufactures billions and billions and billions and billions of transistors at an insanely low cost. And so if you can make, you know, thousands of carbon nanotubes in your lab, in your research lab, that's not going to cut it. You need to figure out how to mass produce them in insanely huge quantities and wired up properly into circuits. That's what the semiconductor industry does, and that is a very high bar to beat. And another way to think about it is silicon technology has literally had, over its lifetime, trillions of dollars invested in it. And none of these alternatives have anything like that. All right, now we already saw that. Okay, junction nanowire transistors. So, I don't know exactly how these work, so I'm just going to go with the analogy. It says, think of a traditional transistor as a bridge that carries electrons across, and junction nanowire transistors as a hose that you step on to cut off the electrons. They do have the property that they work around 3 nanometers, and as they get smaller, they work better, whereas traditional transistors get worse as they get smaller. Again, they have the problem that nobody knows how to mass produce them to compete with silicon. Okay, spintronics. This is a fun idea. Instead of using the presence or absence of electrons to carry binary data, zeros and ones, why not use the spin of the electrons? which is a quantum property of the electrons. A spin field effect transistor design was proposed in 1990. It hasn't been built, but an alternate has been built that uses molybdenum disulfide and graphene. So I've heard that that works, but currently there's no path from the lab to mass manufacturing. So, and it looks like spintronics is more likely to be used just for storage, because you could take electrons and store ones and zeros on the spin and then go and retrieve it later, rather than actually trying to do computations, actually trying to build build a transistor that works with spin instead of charge. Silicon photonics. So the idea with silicon photonics is that instead of using like copper wires to communicate between the different transistors, you convert the signal to light, and you have like a waveguide on the chip that guides the light to where it's supposed to go. Intel has actually gotten this working, and they've actually made some data center products that can use silicon photonics for distances of a few meters. It doesn't work for long distances. It's not going to replace like fiber optic cables or anything like that, because silicon is actually not an ideal material for creating light. And when you do silicon photonics, you're actually using the silicon. I thought I had a thing here. Yeah. Where is it on here? Light. Okay. Yeah. Light is created using an optoelectric modulator that uses controlled changes in the electronic charge to change the refractive index of silicon. So you're actually fiddling with the silicon itself to get it to emit light. And then you use germanium to detect it on the other end. Oh, this is kind of a fun bit here, is that SiO2, which is called silica, because it has a different refractive index, you can actually use it to contain the light in the chip. So I actually have the refractive index is 1.44 for silica and 3.5 for silicon. So the light will actually reflect off the surface of the boundary between the two and stay inside the chip. I think I've covered all that. So MEM resistors and 3D crosspoint is stuff that people ask me about. These are actually just memory technologies, and where they might find application is stuff like AI chips, where you want like a simulated neuron that has state and computation integrated together in hardware. I don't know how 3D crosspoint works. Intel and Micron have kind of kept it a secret and have not they've not revealed the details, but they do say it doesn't use MEM resistors. MEM resistors are memory resistors where the resistance changes depending on the history of the current through the resistor. I think that about covers that. So, okay. And now we're to the last section of the talk, which is the question of when Moore's law will stop. So I got a quote here from Gordon Moore where he's saying about 2025. We're approaching the size of atoms, and that's a fundamental barrier. Okay, so what are the barriers to scaling? Source to drain leakage, limited gate metals, limited options for channel material. So by source to drain leakage, we've talked about this already. You have, when you can't lower the voltage with Dennard scaling, you get current that leaks through. When the transistor's off, there's still current going through it, and that leaks and forms heat and so forth. Limited gate materials. So the gate is a metal oxide. There's this constant kappa, which indicates the it has to do with the way the material responds to electric fields in it. And in order to keep shrinking the gates, they have to keep increasing this kappa dielectric constant. And so they have to keep finding new materials to use for the gates, and that's hard. That's a problem. And limited options for channel material. By that, they just mean, once we've switched from silicon to indium gallium arsenide, what do we do after that? Like, what comes next? And nobody knows. Okay, but we are very far from the ultimate laws of physics. So if you change the question around and say, well, we don't know what all the possible materials are that could be used to make transistors, or what the mechanisms could be, but what do we know about the laws of physics and what it tells us about how information can be processed? Can we figure out what are the ultimate limits of the laws of physics, irrespective of what technology is actually used to do the computing? And a physicist at MIT named Seth Lloyd decided to tackle this question. And he wrote a paper where he talked about the ultimate laptop. Let's see here. Okay, he's talking here about memory space, but I think on the next slide I have the real juicy quote. So he says, it will only take 250 years to make up the 40 orders of magnitude in performance between current computers, which do 10 to the 10 operations per second on 10 to the 10 bits, and our 1 kilogram ultimate laptop that performs 10 to the 51 operations per second on 10 to the 31 bits. And in his quote here, he uses this phrase, extreme regimes. Is it possible to make computation take place in extreme regimes? What does he mean by extreme regimes? He's talking about a computer that has the linear size of its Schwarzschild radius. And the transistors are built on the Planck scale. Now, if this term Schwarzschild radius makes you think black holes, you're on the right track. What you want is your computer to be so dense that it's almost a black hole, but not a black hole. Because if it's actually a black hole, you can't get any information out.
Right.
So it could compute amazing things, but you don't get to know the results, which is probably not what you want.
Is there a trade-off between as it gets bigger, it's harder to get bits out of it, so it becomes prohibitively expensive to do so? Could you
I don't know, but my impression was that the black hole has an event horizon, and once your computer's inside that, you can't get anything out. So it's just a binary interface. It's just
how hard that gets
right. So if you have a black hole, you can get energy out because there's Hawking radiation, but you can't get information out. So your computer on the inside can compute amazing things, and you don't get to know the results because you can't get that information out. So what you want is for your computer to be not quite that dense, but almost, so you can get the results of your computation out. Okay, and then the Planck scale. So what does that mean? Okay, so I've been talking all this time about nanometers, okay? When you go down from nanometers, it goes picometers, then femtometers, then attometers, then zeptometers, then yoctometers, okay? And at that point, we're at 10 to the minus 24. We got to get down to 10 to the minus 35, so we got 4 more to go that don't have any metric prefixes to get down to Planck scale. That's how small that is.
For reference, what's the radius or diameter of a proton?
Well,
He could
It
put
has to be, right?
femtometer, right?
What would it be made of?
It's closer to the femtometer scale.
that
Electrons are 1 atom.
a lot bigger than
is a good question because Well, I know with atoms are on the on picometer scales, and with electrons don't have a precise location. They sort of occupy these orbital clouds on a certain
That's
scale.
a tiny little part of the atom.
And protons.
I think femtometer scale actually, because I remember thinking about this at one point, and I remember sort of it might be like a 100 atometers or 1 femtometer or something along
It
those
says,
lines.
Wolfram Alpha says 0.0015 blah blah femtometers
Okay.
for a proton.
So it's under a femtometer.
Yeah.
So it's atometers.
Yeah. That would be what, 1.5 or something?
Wonder why he gave it femtometers.
I don't know why. I
Yeah.
should have said 1.5.
Get it together, Steven.
I know, really.
Well, the Planck scale is about the size of the universe at the Big Bang. So,
I always just think of it as small as you can go. So,
Oh, cool.
It's amazing what you can do when you're connected to the internet. But I can't make flux go away. So. Okay, DNA. What's our scale here? It's okay. So we're on nanometers. We're on nanometer
it's
scales
not even
here.
that small yet.
Not even small. Water molecule. So we're on the angstroms. So there's atoms. So that should be picometers. There's 10 to the minus 12. So that's picometers. So that's a picometer. That black circle. Femtometers. Okay, so we're down to atometers for a uranium nucleus.
The bottom right-hand corner of the screen shows your scale.
Oh yeah, there you go. Femtometers. So it's showing protons as being femtometer scale, but you said
It's a 10 to the minus.
okay. Range of the weak force, 10 to the minus 17. Quarks.
Whoa. Whoa.
Why
Whoa,
does-
whoa, stop.
Stop. We're down to yoctometer.
It's probably just not that much, so they sped through it.
They just,
Yeah.
yes, there's nothing to see.
This is like
It's
move
just-
along.
we have no idea what's
This
here.
is the Arkansas
Somewhere
of
is,
subatomic
somewhere is
size.
strings, right?
Nothing.
Somewhere is,
There we go. Planck link.
there's the string. There it is.
So what would
Minus
manufacture such a thing? How would you get a transistor from one scale?
Yeah.
Riddle me that.
Yeah.
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 To like
Exactly.
That's what I
strings. I mean, it has to be out pieces.
I think that's my last slide. And after that, I just have all my sources.
I've got a question. So we
That's-
look at the performance.
that's
how
the
we
end.
define this technology. But what are the thoughts around moving beyond the constraints of a binary format of computing? Everything here is binary, right? It's either one or zero.
Binary has proven to be insanely useful.
I get that. But we keep going. If you keep going binary, you keep going to finer and finer and finer. What's the thoughts about moving beyond binary to something that's much more efficient? I don't have the idea. If I did, I'd encourage it.
You know, in researching this, I didn't encounter anything at all. So maybe that's something that people will look into once
Yeah, I mean, you
progress
keep
has
going
come to a
zero
dead stop
then you're
with
thinking about
binary.
games and what's positive, what's negative. At some point, looking at
Well, what about DNA and what about quantum?
Um,
Where does quantum fit into it? Quantum's not binary.
So DNA has been used for storage and has shown to have longer life than most storage media. You could store something on DNA and have it conceivably last 1 million years, which is pretty hard with, if you think about like hard disks or optical disks or anything, it degrades much faster than that. And you have to constantly copy it to fresh media. DNA currently is pretty messy to work with though, because you have to put your data, you have to sequence it on DNA, and then to get your data back, you have to sequence it and reassemble. You know, all of the tools that people use for like reassembling genomes and stuff, you have to incorporate all that to get your data back. So it's currently not easy to get it back. That might improve in the future. So that's the first half of your question, DNA. Quantum. So quantum computing is something that is widely misunderstood, I think. There are a lot of people who think that quantum computing is a continuation of Moore's law, when in fact quantum computing is a different type of computing that is incredibly effective at certain problems, and not useful at all for most of the mundane things that we use computers for. Like, you wouldn't want a quantum computer to watch a YouTube video. There'd be no point in that. But you could use a quantum computer to break encryption, for example. That's something conventional computers can't do. And you could use it to simulate quantum systems. So if you think about, this is probably what will be the most effective use of it, because if you think about simulating chemistry with conventional computers, we're always using these approximation models. And it's very computationally expensive to take the fundamental equations from quantum physics and use that to compute the properties of a molecule and what it will do. But if you actually build the molecule in reality, nature will figure out what it does instantly, right? It computes the solution instantly. And if you had a quantum computer with a sufficiently large number of qubits, you could do the same thing. You could compute the solution just as fast. You could compute the solution to a quantum problem the same speed that nature itself can. The key thing there is to have enough qubits, and that turns out to be really tricky, because in order for the computation to work, all of the qubits have to be entangled simultaneously. And any little tiny thing, like thermal noise or any little jiggle, will cause the entanglement to stop. It will cause the, I'm trying to remember the terminology that you use in quantum physics. You have a collapse of the waveforms. So it's really hard to explain.
You still wind up with ones and zeros in the end of the computation too, right? You don't get
You do because qubits are binary.
Right.
Right.
I mean, they're indeterminate until the computation is made. And then
Until it's
You
completed.
still get ones and zeros. You don't get other numbers.
Yes. But you also don't get intermediate values. Like, you have to compute the whole computation as kind of a one-shot deal with all your qubits entangled.
Right.
And any little thing will ruin it.
Right.
So, and I don't know how many qubits they're up to currently. It's kind of confusing because they have some quantum computers that are basically straightforward implementations of a very small number of qubits, like 7-qubit computers or something. And then there's others. There's like the D-wave computers, which use some other method. I'm not really sure how they work. But I haven't heard of any breakthrough results from the D-wave computers, and they've been around for many years at this point.
So we do one more?
Running out of time here, maybe just.
Yeah, one more.
Okay.
Well, I don't know, you choose.
Do you see AI helping us along the way? Haven't seen any effects of that already. Using AI to improve the speeds, come up with new designs.
I guess the simple answer would be no, but I expect that AI algorithms will be used in the electronic design automation software that I was referring to earlier, like the software made by Synoptics and companies like that.
Yeah, there
Cadence
might be,
design.
and also on the chemistry side, so recently there was a breakthrough where they put in all the parameters that they wanted a substance to have, and the computer came up with a new
Oh,
substance.
that's true. There is a lot of machine learning stuff being used for chemistry, for fundamental chemistry. Thank you. That's a very good point. So I guess that's it. So we'll wrap it up.
Yeah. Thank you very much. I said breathtakingly thorough. And I think
Didn't disappoint.
did not disappoint.